the hydrogen atom. So this is where we're actually going with this. But here, this is general for any two-body type problem here. Oops, it shouldn't be the mass, that should be the reduced mass. So mu, there we go. So again, we just have two bodies. In this case, we're looking at a proton and an electron, but whatever. Doesn't really have to be, just whatever two-body problem that we're looking at. And basically what we showed was that we ended up with the Hamiltonian split up into two different parts when we were working in the relative position and the center of mass position frame. All right. So this was our basis states that we're using here. So this thing split up into two parts, which was the Hamiltonian of the center of mass, which was just the kinetic energy, plus the Hamiltonian of the relative, which is then the momentum of the relative coordinate divided by twice the reduced mass. So again, mu here is the reduced mass, so that's m1, m2 divided by m1 plus m2, plus then the binding potential energy, which only depends on the relative position between the two. And here we're working specifically in the center of mass frame, which means that the center of mass momentum is equal to 0. So in that case, the Hamiltonian of the center of mass is also equal to 0. So the total Hamiltonian then is just a relative Hamiltonian. Oh, good. So that's where we finished last time. So from here, we're going to pick up with angular momentum. So remember that in classical mechanics, angular momentum is L. So here we're talking about the orbital angular momentum. Is equal to r cross p. In quantum mechanics, it's exactly the same thing. We're just going to promote now everything into an operator. So this is now the angular momentum vector operator, the position vector operator crossed by the momentum vector operator, or in component form, this is going to be Li is equal to epsilon ijk, the position operator J times the momentum operator K. Okay, so this is its component form. So I'll skip the proof of all this. This is in the notes that I posted, or the book that's posted. So, but basically what you can do is you can go through and you can show that the angular momentum actually commutes with the momentum squared. And the angular momentum computes with specifically the position, in this case then the potential, which means that it commutes then with the total Hamiltonian. So the angular momentum commutes with the Hamiltonian, which simply means that the time rate of change of the expectation value of the angular momentum then is equal to 0, which gives us conservation of angular momentum. So in classical mechanics, for the two-body problem, we have conservation of angular momentum, and in quantum mechanics, we also have conservation of angular momentum. So it's nice to see that that carries over from classical mechanics. And the fact that these things commute basically just tells us that these guys are rotationally invariant, meaning that if this was my position vector, right, I can rotate this thing any direction that I want to without changing the length of the position vector. So that's basically all this thing means. So here we're creating what's known as a two-sphere, where the two-sphere basically just means that it's a two-dimensional sphere. So it's at a fixed radius. So if this was my radial vector, say pointing off in this direction, I could rotate this anywhere along this two-dimensional sphere without changing the length of this. So this is what's actually called a two-sphere. So, and that's going to lead us to the spherical harmonics. So we'll talk about those eventually. Okay. So good. So spherical harmonics are actually just the basis functions for a two-sphere. But we'll get there. Life will be fine. So basically, let's kind of recap what we have. So what we want to do now is find basis functions for the two-body problem, right? Now, what we know is that the Hamiltonian commutes with the momentum squared, in this case, the relative momentum squared. We know it commutes with the angular momentum squared. It also commutes with the z portion of the angular momentum. So that means we can find a basis, which is a simultaneous eigenstate of all of these different things. So basically, we follow what we did in chapter 4. What we did in chapter 4 was we took the fact that this guy, right, L squared, commuted with LZ, but all the different i's did not commute with each other, because if we had Li with Lj, this was equal to IH bar epsilon ij k lk, right? So from here, using this information, what we did is we created a simultaneous eigenstate from L squared and Lz, which we called Lm. So that if we acted L squared onto Lm, that then gave us L times L plus 1 times h bar squared times then Lm. And if we acted Lz onto Lm, that then gave us mh bar times Lm. So basically, we want to do the same thing here. But now, since we have the Hamiltonian also commutes with all of this stuff, we're going to take that same Lm, which has the same properties as it has here, but now add one more piece to it, which is now the energy. So our total basis function for the two-body problem then is going to be labeled by the energy, the angular momentum, and the z portion of the angular momentum. So this one comes from the Hamiltonian, this one comes from L squared, and then this one's going to come from Lz. So this is our simultaneous eigenstates, which has to do with the Hamiltonian, the angular momentum squared, and Lz. So we're just focusing on these three here. Nice. Oh, including this guy too. So, following what we said over here, what this means then is that if the Hamiltonian acts then onto our simultaneous eigenstate, this just pulls out the energy of our simultaneous eigenstates. So acting our Hamiltonian onto there just pulls out the energy, tells us the energy of that eigenstate is Lm. If we act on it with L squared, energy times Lm, then again, following what we have here, this just pulls out the angular momentum times the angular momentum plus 1 times h bar squared times Elm. And finally, acting Lz onto all this just pulls out the magnetic quantum number, or the z portion of the angular momentum, times h bar times Elm. So good. So basically, what we want to do now is use the simultaneous eigenstates to then look at the stationary states of this particular two-body Hamiltonian. So again, our Hamiltonian is equal to, again, p vector squared divided by 2 mu plus v r. And again, what we want to do now is use these simultaneous eigenstates to actually then determine what are the stationary states of this particular Hamiltonian. Okay. So we're going to project this into position space. So we want to know, what is the position space version of this? Now, one thing that's kind of interesting here, and we're going to show this, is the fact that the Hamiltonian here actually is a function of L squared. So it turns out that inside of the Hamiltonian, inside of here, there's actually an L squared buried inside of here. So what we want to do now is actually pull that out, so that way we can use this particular simultaneous eigenstates to then find the energy eigenstates for our Hamiltonian here. So let's do that. So the way we're going to do that is, let's start off with L squared. So I'm going to start off with one component of L squared. So let's look at this guy. So let's look at the ith components of this guy squared. So this guy is going to be equal to epsilon ijk of then xj pk times then epsilon ilm then xl. Oops, let's write a j. So I'm doing this in component form. So XL PM. Guys doing okay?
Quick question, Professor.
Sure.
The different indices there.
Yes.
What? Oh, okay. Never mind. I think I see now.
Okay. Yeah. So this epsilon has the I. This one also has the I, and that comes from the fact that L squared is just a dot product. right? So if I'm looking at L dot L, then this is then equal to Li times Li.
Okay.
So those two things have to be the same. Otherwise, since this one is summed over this guy, this one's summed over this one, I then have to have different indices for these two. So that's why they have different indices. Yeah, so this one is an Lm to go with these two, or this one was a Jk to go with this one. Does that kind of answer your question?
Yeah.
Okay, good. So now here, since all of this is actually just components, we can now move things around. So what I'm going to do is I'm going to pull this epsilon to this location and then use an identity. So I'm going to write this as epsilon ijk times epsilon ilm times xj pk xl pm. So let's write it that way. Now the identity comes in that if I have epsilon ijk times epsilon ilm, this is equal to the Kronecker delta function of these two, so j with L, times the Kronecker delta function of k with m, minus then the Kronecker delta function of now the mixture of the two. So now it's going to go j with m times the Kronecker delta function then with k with L. Okay. So this is an identity that you can find on something like Wikipedia, or you can prove it if you want. It's kind of fun to prove it, but that's fine. You don't have to. So, but just know that this guy is actually just an identity that we're going to use. So good. So let's insert that identity here. So this is going to become delta JL delta KM minus delta JM delta KL, all times that other stuff. So KJ, PK, XL, PM. So now we're simply going to multiply these things in here and basically just distribute. So this is going to become, so I'm going to get a delta JL delta KM acting onto XJ, PK, XL, PM minus delta JM delta KL times XJ, PK, XL, PM. So remember here, even though I'm not writing a sum out in front of all this, but what we really mean is that we're actually summing over all of these different things. So implied outside of here is a sum. This is what's called Einstein summation notation. I think we talked about this before. But basically all I'm going to do now is what? This delta function is going to force all the j's to become l's, or all the l's to become j's, whichever way that you actually want to look at it. Which basically means that when I multiply this through, this delta function here forces this j to become an L, or this L to become a j, which means that I can rewrite this then as xj times xj. And then this one's going to force the k to become an m, or an m to become a k. So this is now going to become pk times then pk. But this thing here is simply a dot product, right? Same thing as over here. So anytime I have repeated indices, this is actually a dot product. So this guy is actually the same thing then as x squared times then p squared. So that's what this first term becomes. Suppose I should write these as vectors. There we go. Now let's do the same thing over here. So I'm going to get a minus. So here I'm going to have a j and an m equal to each other. So here, this j and this m have to be the same. So let's write that here. So basically what has to happen here is I'm going to get an xj times a p m. I'm sorry, it should become a j. There we go. RB. PJ, there we go. So that's also a dot product. Times, now I'm going to get k has to equal L. So what has to happen then is that this one has to equal this one. So this is now going to give me a PK times an XK. That okay? Now here, notice that this term here is the same thing as this term, except it's out of order. Now, when it came to classical mechanics, for example, it doesn't matter the order in which I'm multiplying these because we don't have things like the commutation relation that we have to worry about. But in quantum mechanics, the order of these things actually matters because they are operators. So we now have to use our commutation relation, which says that what? If I take x commuting with p, this guy is equal to what? Minus I h bar. So this means then that's what? X, or let's do it this way. Yeah, let's do it this way. Xk pk minus then a, what? Pk xk is then equal to a minus I h bar. Guys doing okay? Which is also equal to the commutation relation between x, k, p, k. Good. So basically here, all this thing means is what? If I want to replace this guy with this guy, we're then going to have to rewrite pk xk as then being xk pk minus then the commutation relation between x and p. Okay. Doing okay? So let's plug that in here. So this now is going to become minus, so let's do it this way. So it's going to become an xj pj times then xk pk minus the commutation relation then between xk with pk. So let's multiply everything through. So this thing again is just going to become simply an IH bar. Actually, this is positive IH bar, not negative IH bar. Sorry about that. Positive IH bar. I always get that backwards. Good. So let's multiply everything through. So that negative then kills off this negative, and this is going to become a positive. So let's multiply everything through. So finally, this gives me then x vector squared hat p vector squared hat minus then, this is the dot product between x and p. This is also a dot product between x and p. So then I get a minus dot product between x vector hat dotted with p vector hat squared plus IH bar times then x vector hat dotted with p vector hat. Okay. Or if I turn these things back into r's, finally what this tells me then is that L squared vector hat is then equal to R vector squared hat times P vector squared hat minus the dot product between R and P, quantity squared, plus IH bar times R vector hat dotted with P vector hat. Guys doing okay? So now what we want to do is find the position space representation then of L squared. So basically what we want to consider now is R vector L hat squared psi. So basically what we're going to do is what? Find our matrix representation for this guy. And that guy is going to be dependent on then p squared. So let's see how that actually works. So this is going to be equal to R vector, and if I insert this thing, it'll be R vector hat squared, p vector hat squared minus R vector dotted with p, quantity squared, can't forget all my hats, plus IH bar, R dot p psi. So let's look at all this term by term. Okay, so first let's consider this term. So let's look at R vector hat squared, P vector hat squared psi. Okay. So here what I'm going to do then is operate R hat onto R position vector. And remember that R vector hat acting onto r vector is simply equal to r vector times r vector. Right, so basically all this thing is doing is it's pulling out the position at which this thing is at. So when I act it to the left, this also pulls out just the position. And then when I do it again, it pulls out a second portion of the position, which means this is the same thing then as simply r vector squared, and then the inner product between r p vector hat squared and psi. Okay? So basically this is the kinetic energy term times that r squared term. So this is the portion of the Hamiltonian which deals with the kinetic energy. So this is the translational kinetic energy. Okay. That's doing okay? I'll take stunned silence as a good thing. Okay, so now let's look at this term. So let's do this term here. So let's go to our next page. So next time we're going to look at then is r vector hat dotted with p vector hat psi. Okay, and ignore the IH bar for now. So here, same thing. What I'm going to do is, again, act the r onto this side, which is going to pull out just a position vector. So this is going to be equal to r vector dotted with the inner product of r vector p hat psi. But we know from what, chapter 6, and the beginning part of this chapter is that what? When I act p then onto psi, what I get is a negative IH bar, right, times the gradient operator. So this is going to be equal to minus IH bar, r vector dotted with the gradient operator, acting then onto r psi. So this was one of our generalizations from earlier. But the r hat, or the r vector dotted with the gradient operator, basically is only going to pick out the portion which points in the r direction, which means this is the same thing then as minus IH bar r times the partial with respect to r of then r psi. Okay. So finally, that brings us to the last term, which is then r vector, and now we have this thing squared. That's squared psi. Well, following what we did here, if one of these guys gives this, then two of these has to give two of these guys, right? So basically, all we're going to have then is what? One of these, so minus IH bar r partial r, times the second one, minus IH bar r partial r, all acting then onto r psi. So multiply this out. This gives me a negative sign because I get a negative I times a negative I, which is negative 1, times h bar squared, times r partial r times r partial r, acting then into r psi. Well, let's multiply this out. So this guy is going to be equal to minus h bar squared times r times. So this guy, when I multiply onto it first, it's going to make this guy simply equal to 1. So I'm going to get a partial r. And then when I multiply it onto this guy, I'm going to get a plus r partial r squared, all acting onto r psi. Okay. So good. So using all these pieces, let's put everything back together. So what this thing says then is that what? So let's go back to here. So if I have r L hat squared psi, then that's equal to the first term, which is simply r squared times then r p hat squared psi. Am I missing h bar? No, okay, good. And then I get a plus, but this guy's going to make it minus. So I'm going to get then a, let's do it this way. So I'm going to get a minus IH bar squared times then r partial r, r psi, And then I'm going to get a minus sign from this guy. So I'm going to get then a minus h bar squared r times then partial r plus r partial squared times r psi. Okay. Guys doing okay? Now this guy's going to give me a plus sign because I'm going to get a minus I, or actually get an I squared, which is going to make that a plus. So finally, this term is going to become plus h bar squared r partial r psi. Okay.
Professor,
What's that?
oh, never mind. Sorry.
Oh, you're fine. Actually, this term should be the same as this term. Okay, where do I go wrong with my signs? Let's see here.
You forget the.
Oh, because I added it, not subtracted it. Sorry about that. Okay, let's go back. Sorry, this one should have been subtracted, so with a plus sign. Sorry about that. Okay. Yeah, because I got a minus. There we go. So that makes it a positive sign. So finally, this thing is going to become what? R squared R p vector hat squared psi plus, so I'm going to get an h bar squared times r partial r squared plus 2 r partial r. Pull my r out front. Okay, so let me put this r. That's okay. Let me get rid of this r here. Trying to keep track of all these terms. This should be an r squared. There we go. 2r. Good. Times then r psi. Okay. So good. So basically from here, what this says then is that, again, this is pretty much the kinetic energy term of the Hamiltonian, which means if I solve for this, I'm simply going to take these two things and subtract them over here and then divide by 1 over r squared, right? Or divide by r squared. So finally, from here, what I get then is that r p vector hat squared psi is then equal to, so let me do it in this fashion. So this is going to give me a negative h bar squared times, so now I'm going to get a partial r squared plus 2 divided by r partial r, all acting onto r psi, and then I'm going to get a plus 1 over r squared r l hat squared psi. So again, so basically, again, since this is part of the Hamiltonian, what this means is that, again, the Hamiltonian actually has an L squared buried inside of it because the momentum actually has an L squared buried inside of it. So this thing here, again, is pretty much the translational kinetic energy, but this part here is simply the rotational kinetic energy. So let's put all this back into our Hamiltonian. So finally, we can then say that's what our Hamiltonian, if I do r psi, is then equal to 1 over 2 mu times then r p hat squared psi plus r v r hat psi. Now, using what we just did here, this thing is actually then equal to minus h bar squared divided by 2 mu, right, times then, so this is going to give me a partial r squared plus 2 over r times then r psi plus, I'm going to get a 1 over 2 mu, and then this is going to give me a r l squared psi, and then finally I get a plus r v of r magnitude psi. Okay. So overall, this is then what my Hamiltonian is going to become. So again, this thing here is simply the translational kinetic energy.
Real quick question, Professor.
Sure.
Is there a dr, partial r after that 1 over
Oh
r
yeah, there
term?
should be one right here. Yes, good. Thank you. Sorry about that. So this is, yeah, our translational kinetic energy. And then this part here is the rotational kinetic energy. And then this part here is simply the potential. So all this is saying then is that this is still equal to the total kinetic energy, which is now the translational plus the rotational kinetic energy, plus then the potential term. But here, this is the rotational kinetic energy of simply a point mass, right? Or a point mass which has a reduced angular momentum or reduced mass of mu, right? Because remember, the angular momentum of a point object is simply equal, well, let's see here. The rotational kinetic energy, let's do it that way. We always call that T, don't we? Okay, we forget all my stuff. So rotational kinetic energy, remember, is equal to L squared divided by twice the mass, right, for a point mass. So in this case, all we're doing is simply replacing the mass with the reduced mass. So again, so this thing is acting just like a point mass, which is rotating, and then it has some sort of translational kinetic energy to it as well. So now that we've written that far, what we want to do now is apply our simultaneous eigenstates. So here we're going to take psi is simply then equal to Elm, and then go ahead and plug that in for psi into all these different regions. So when I do that, what'll happen then again is that L squared acting onto psi is going to pull out the L times L plus 1 times h bar squared. This guy here, I'm simply going to act this onto him, which is now going to pull out simply the position. So finally, and we also know that the Hamiltonian on the left-hand side acting onto the state is going to pull out the energy. So if I replace this into all these different locations, what I finally get then is that the energy times ReLm is then equal to minus h bar squared divided by 2m times partial r squared plus 2 over r partial r plus L times L plus 1 times h bar squared divided by 2 mu plus the potential, which now only depends on the magnitude of the position. All acting onto R, E, L, M. Actually, this R I could just call a regular R. Oops. You can draw that line over there. There we go. Just call that R. Same thing as this R. Oh, good. So basically, this now is the energy eigenstates for our two-body problem. Good. So this thing depends only on the radial position and only depends on the angular momentum value. It doesn't depend on anything about M. So the other thing we can see from here is that since R is rotationally invariant, everything else here doesn't depend on rotation at all either, then this thing is actually only dependent on R. So this entire thing only depends on R, not theta and phi. The other thing we can actually see from here is that it's also independent of M. Right? Remember, M is the portion which goes with LZ. So the reason for that is because this thing has complete spherical symmetry, which means that here, since this thing has spherical symmetry, there's no preferred axis that this thing is actually rotating about, unlike a cylinder or something like an electric field or magnetic field. There's no preferred axis, which means that there's complete spherical symmetry, which means that it has complete rotational symmetry to it, which is why this thing is completely independent of M. If there was M dependence to it, then there would have to be something which breaks the spherical symmetry. Like I said, in that case, it would have to be something like a cylinder, which doesn't have complete spherical symmetry to it, or it'd have to have something like an electric field, which was pointing in some particular direction, something like that would then have to break that M independence, meaning that it doesn't have complete spherical symmetry to it. But here, since this thing is completely independent of M and theta and phi, that's just a manifestation of the fact that this thing has spherical symmetry to it, which again means that the Hamiltonian commutes with the angular momentum squared. So this thing has conservation of angular momentum, which means it doesn't matter how we have to actually rotate this thing, it will always be the same. Good. So how do we actually solve this guy? Well, first we need to know what the potential is, but we'll talk about that later. But basically, here we would use separation of variables. And since our Hamiltonian here, or at least our equation that we have to solve, our differential equation, is independent of theta and phi, that then implies to us we can use separation of variables to then write what? The inner product of R, E, L, and M as now being a product of three functions, where one only depends on the radial portion, one depends on theta, and then the other one depends on phi. And we'll talk about this. I already mentioned this, but these two are actually not independent from each other. These two are actually coupled together, and these are actually the Ylms that we talked about in math methods. So in actuality, this thing is actually equal to R times the Ylms. So if we use this ansatz and we plug this then into our differential equation here, since nothing depends on theta or phi, all that's going to happen is this guy's going to pass right through both sides, which means this guy's going to divide right out, which means our equation, our differential equation, then simplifies to E times R of R, then is equal to minus h bar squared divided by 2m times then, again, partial r squared plus 2 over r. Actually, these guys become full derivatives now because nothing depends on theta or phi. Everything's only r dependent, so it's going to be the second derivative plus 2 divided by r times the first derivative plus h bar squared times L plus 1 divided by 2 mu plus V of R, all acting onto R of R. These should be mu's, not m's. There we go. I'm going to keep writing m, not that I mean to. It's just going to happen. I'm doing okay. So basically, what we've done then is we've actually shown that the quantum two-body problem actually reduces to a one-dimensional single-body problem. So in this case, our quantum mechanical two-body problem in 3 dimensions actually reduces now down to a one-body 1D problem. Again, this is exactly the same thing that happens in classical mechanics. So in classical mechanics, if we had something like, again, the sun, and then we were looking at the earth, right, something like this in a gravitational sense, again, our two-body problem basically just comes down to a one-body problem of the sun, basically. Because here, again, we have the reduced mass. The reduced mass then is going to be primarily dominated by the sun, where here this is also going to be dominated then by the proton. So even in classical mechanics, this was the result that we had in classical mechanics. This term was a little bit different, but other than that, it's exactly the same. The only thing that's basically quantum mechanics here is kind of this term here. So you don't really get this term in classical mechanics. You get a term similar to that, but not exactly that guy. So good. So it turns out we can actually simplify this by introducing a new variable. So let's introduce a new variable. So let's introduce. So here I'm going to write R of R then is equal to U of R divided by R. So I'm introducing this new quantity U, which is related to R, or capital R, this way. So what happens then? So let's look at this derivative term here. Let's see how this actually simplifies our life. So let's look at the second derivative of u divided by r plus 2r times the first derivative of u divided by r. So let's look at this term. So let's look at this one first. So this is a product of two functions, right? So this is going to be what? The derivative of the first. So let's write it this way, ddr of the derivative of the first times the second plus the derivative of the second times the first. So I'm going to write this then as u prime divided by r minus u divided by r squared. Where here I'm writing u prime then is equal to du dr. Just kind of be a little bit lazy. Plus 2 divided by r times the same term, right? So this is now a u prime divided by r minus a u divided by r squared. Now if I look at this term, so now I'm going to have to take the derivative again. So this is going to be equal to then u double prime divided by r minus u prime divided by r squared. So that's the two derivatives from this term. And I'm going to take a derivative of this, so this gives me a minus u prime divided by r squared. And I'm going to get a plus. So I get a plus 2 u divided by r cubed, right? So that's that term. Now I'll expand this term. So then I'm going to get a plus 2 u prime over r squared minus 2 u over r cubed. That's it, okay? So notice this term here is the same as this term with an opposite sign. These two terms combine together to give me a minus 2. That's the same thing as this term. So this term and these two terms are going to cancel, which means that I'm left with then 1 over r, the second derivative of u with respect to r. So by introducing this new variable, this u, we can actually reduce this thing down to a single derivative, which now just depends on u instead. So using this, finally we can reduce our differential equation to, so finally we're going to get a minus h bar squared divided by 2 mu times the second derivative with respect to r plus L times L plus 1 times h bar squared divided by 2 mu plus the potential, which depends only on r, all acting then onto u of r, which is then equal to E times u. So finally, this is the differential equation that we have to solve. So this is our two-body problem differential equation for the radial position. Of the relative coordinate. So again, even though we have a two-body problem, this thing is actually only a one-dimensional differential equation that we have to solve. Again, this thing is only a 1D differential equation, which only depends on r, which again is the relative coordinate. So here, this thing we can actually write as minus h bar squared divided by 2 mu times the second derivative with respect to r plus some effective potential, all acting then onto u is equal to the energy times u, or in this case our effective potential is then equal to L times L plus 1 times h bar squared divided by 2 mu plus v of r. So again, this is pretty much exactly the same thing that we would get in classical mechanics. Again, this thing comes from the, what, Coulombic, well, not the Coulombic term, the centrifugal term. And then this one would be the Coulombic term if I was talking about the hydrogen atom, but this is basically just the regular potential term. So the binding potential then is the, what, centrifugal term plus then the potential term in classical mechanics. So this thing, again, reduces with effective potential, pretty much exactly the same type of formula. So good. You guys doing okay so far? You guys caught up, or do I need to go backwards?
I think I'm caught up.
Yeah, I'm caught up.
You're caught up too? Okay. Now, one thing to point out here is that even though it seems like M is not important, but it turns out M actually is important. So even though our differential equation is independent of M, M is still important. So basically the reason for that is, remember that for a given L, there are 2L plus 1 M possible M states, right? So for a given L, there are 2L plus 1 possible M states. So even though our differential equation doesn't depend on M, since again, it's completely spherically symmetric, it has complete spherical rotational symmetry or invariance to it, the M value is still important because when I specify the states, I still have to specify the M value because there are 2L plus 1 possible different L values. So to fully specify the state, then we do have to specify what M is to actually know exactly what the state is. Since this thing is independent of M, it could have any one of these 2L plus 1 possible states. So to fully specify the states, we need to specify M. Because otherwise there's that ambiguity, we don't exactly know which one it happens to be. Doing okay? So good. So the next thing we want to talk about is L hat in spherical coordinates and position space. So we want the position space representation. So position space representation of L vector hat in spherical coordinates. So we need to know what this guy is. So here, since we're working in spherical coordinates, what we're going to do is we're going to take our basis states. Right? Remember our R vector, which we said was equal to X, Y, and Z. And we're now going to write this in spherical coordinates. So this is going to be dependent on R, theta, and phi. So what happens if I act a rotation operator about d phi in the k hat direction, for example, onto the state of R, theta, phi? Well, since this thing is only changing phi, what that's going to do is it's just going to become equal to then R, theta, phi plus d phi. So basically all I'm going to do is add a d phi to the phi term. Now, the broad version of this then is going to be equal to what? R theta phi being acted on by R dagger d phi k. Remember, I'd have to take a dagger both sides, so this guy becomes the dagger, which is then equal to r phi, theta phi plus d phi. So that if I acted r theta phi on r d phi k, then that's just going to move it in the negative direction. So r theta phi minus d phi. Okay. So good. So let's see what actually happens if we rotate our states. So let's take our r theta phi, r d phi k, and act that onto the state psi. Well, using this, we know that's going to move this guy by a negative d phi. So this guy's going to be equal to then r theta phi minus d phi psi. Or if I write this as a wave function, this is equal to psi of r theta phi minus d phi. Now here, if we assume that d phi is much, much smaller than phi here, we can actually do a Taylor series expansion onto here. So here we're going to assume that d phi is much, much smaller than phi. And we're going to go ahead and do a Taylor series expansion about d phi here. So this thing's going to be approximately then equal to psi of r theta phi minus, so this is going to give me a d phi, and I'm going to get the partial with respect to phi of then psi of r theta phi. So let's rewrite this in Broadcat notation. So this is then equal to r theta phi inner product with psi minus, so this is going to give me a d phi partial phi of then r theta phi psi. Okay. There we go. Now, why am I doing this? Well, remember that for small deviations of the angle phi, r d phi k hat is approximately equal to 1 minus Lz times what? I divided by h bar times d phi. Okay. So basically, if I look at this here and I look at this guy here, what I can then identify is that this derivative here goes along then with Lz. So what has to be true is then if I compare this side to this side, what has to be true then is that what? Minus I Lz divided by h bar must then be equal to minus the partial derivative with respect to phi. So what this tells me then is that Lz then is then equal to what? So this is going to be equal to h bar divided by I times the partial derivative with respect to phi, or equal to minus I h bar partial derivative with respect to phi. So basically, by looking at this, what this tells me then is that in spherical coordinates, the position space representation then of the z component of the angular momentum is then equal to negative IH bar times the derivative in respect to that angle. Now, if we compare that with the momentum operator, so remember the momentum operator, say position in the x direction was equal to minus IH bar partial x. So this thing has exactly the same type of structure as the momentum operator. Everyone's doing okay? Now, since this thing here has nothing to do with position, what we can do then is what? Look at only the spherical parts of our simultaneous eigenstates, which basically means that if we project this onto position space, right, in spherical coordinates, get theta, not a phi. Phi, there we go. Lz, Lm We also know this guy is what? An eigenstate of him, which then has what? mh bar times r theta phi Lm. But using what we just did, the left-hand side is also written as minus ih bar partial phi inner product between r theta phi L and m must be equal to mh bar r theta phi L m. So basically, what this is going to do is it's going to give us then a what? First order differential equation to find out what this function is. Right? So let's go ahead and do that. So if I solve this guy, what this tells me then is that r theta phi L and m. So this structure here simply gives me a what? Gives me a natural log. So this is then equal to E m phi times then r theta phi L m. Forgot my I. There we go. Because here the h bars are canceling out. Guys doing okay? Now, for this thing to be true, as we talked about from math methods, this thing then has to be single valued. So for this thing to be single valued, what has to be true then is that what? Phi has to then go as phi plus 2m pi, right? Where m in this case is then equal to 0, plus or minus 1, plus or minus 2, etc. Right? For this thing to be single valued. Since m goes as an integer, and we know that the L values, there are 2L plus 1 different L values for each m, what this basically tells us then is that L must be an integer. Now what's kind of interesting about this is that what? For the two-body problem then, the allowed value L values are actually integers, so for our two-body problem. Unlike for what? The single value of a proton or an electron, that thing had L values which were equal to half integers. So this was for the one-body problem. So this just goes back to that addition of angular momentum that we talked about before, which basically means that what? If I took two spin 1/2 particles, which had allowed value values which were this way, we then are going to create some sort of other particle, which then has either 0 or 1 or etc. But basically we go from fermions to then bosons, right? So basically all this thing is saying is that our hydrogen atom or a two-body problem here has to be bosonic, where the individual particles are actually then fermionic. So again, this just goes back to that addition of angular momentum that we talked about before. So here, even though we're building it from multiple things which have what, half integer spin, this thing then has to have full integer spin. You guys doing okay? So far so good. So good. So we have one coordinate of the angular momentum in position space. We now need the other two coordinates in position space. So basically here, to derive those, let's use that L vector hat, again, is equal to R vector hat crossed by P. P, again, in position space is equal to what? H bar divided by I times the gradient. So this thing is actually equal to R vector hat crossed by, so I'm going to get an h bar divided by I times then the gradient operator. So here, since I'm working in spherical coordinates, we're going to write this guy into spherical coordinates. So this thing then is going to be equal to R in the ER hat direction, crossed then by ER hat times partial R plus E theta hat times 1 over R E theta plus E phi hat times 1 over r times sine of theta partial phi hat, partial phi. Now when I cross this thing here kills off this one, so there is no r component. When I do E cross, or ER cross E theta, that then gives me an E phi. And then when I do an ER cross an E phi, that then gives me a negative E theta. So this thing is simply going to become equal to R. So actually this R is going to cancel out both of those two R's. So those R's are going to go away. So this thing now simply becomes what? This term, but now it's going to point in the phi hat direction, and this term, which is now going to point in the negative theta hat direction. So this is going to give me a, oh, I forgot my IH bar here. All times minus IH bar. Good. So I get a minus IH bar times. So I'm going to get a, in the phi hat direction, a partial theta, and then I get a minus 1 over sine of theta, partial phi, all in the theta hat direction. So basically from here, what we're going to do is, I'll sketch out what we're going to do. I'm not actually going to go through all the algebra here, but basically all we're going to do is we're going to rewrite each one of these different directions. So the theta hat direction and the phi hat direction in Cartesian coordinates. So if I write in Cartesian coordinates, this becomes in the I hat direction, cosine of theta, cosine of phi, plus the j hat direction, I get a cosine theta, sine of phi. In the k hat direction, I get a sine of phi. And then for the phi hat direction, this guy's equal to minus I hat sine of phi plus j cosine of phi. So basically, by using these guys then, we're going to plug those guys back into these. And then basically combine all like terms together and then put this into Cartesian coordinates. So if I do that, give me the overall value what this thing should be. So I get an L vector hat then is equal to minus IH bar times in the I hat direction. Get a minus sine of phi times the partial with respect to theta, minus then cotangent of theta, cosine of phi times partial in the phi hat direction, plus in the j hat direction, cosine phi partial with respect to theta, minus cotangent theta, sine of phi, partial phi. Finally, I get a plus k hat, partial phi. From here, we can then get an L vector hat squared. So basically, we're just going to dot all these things together. So I'm going to get this guy squared, and then this guy squared. So this is going to give me a minus h bar squared times, combining like terms together. So I get a 1 over sine of theta, partial theta, sine theta, partial theta, plus 1 over sine squared theta partial squared phi. So this is my angular momentum squared in position space in spherical coordinates. So this is the final result that we want. Whew. Guys doing okay? Where did I lose you, William?
On the first page, I think.
Gotcha. You want to go back and talk about anything?
No, I don't think so. I'll figure something out.
Okay. So, as usual, the gist is that it works pretty much exactly the same way as classical mechanics. I guess that's the best way you can say it. All right, so good. So let's kind of rehash. So, as I mentioned, so basically due to our spherical symmetry, what we can now say is that if I project onto, so let's look at just the spherical portion of our system. So let's look at the spherical portion. If I then project the theta phi Lm, so basically if I project the portion which deals with the angular momentum then into position space, but only the spherical portion, then this thing actually gives me the Ylms. So again, these guys are simply the spherical harmonics. So this says then that the full energy eigenstates are then equal to that radial portion times then the Ylms, which depend on theta and phi, or this is then equal to, for u of r divided by r Ylms. Right? So this is my total wave function. So these are my, again, energy eigenstates or my stationary states. These are my energy eigenstates. So that depends basically just on the radial piece times then our spherical harmonics. So our eigenfunctions here, so these are our energy eigenstates or our energy eigenfunctions. So our eigenfunctions have to be normalized. So we know that these things must be normalized. So I have to integrate this d3r of r theta phi Elm must be equal to then the integral d3r of then, I write it this way, r of r Ylm theta phi, and this thing has to be equal to 1 since this thing must be normalized. So this is our normalization condition. Now, the nice thing about this is since the radial piece only depends on the radial, the angular piece only depends on the angular, what this means then is that these two things are actually going to be normalized separately. So what'll happen here is we can write d3r being equal to then what? R squared times dr times sine of theta d phi, but sine of theta d phi is also what's known as d omega, which is what's known as the arc length, or sorry, the solid angle. So basically here, since d3r splits up into a radial portion and an angular portion, and our wave function is split into a radial portion and an angular portion, that means these two things can actually be normalized independently from each other. So this is also going to be equal to the integral of dr r squared r. Good. Oh, sorry. There should be brackets around here. Sorry. For normalization, it has to be modulus of this guy squared. Sorry about that. Good. So this should be the modulus of him squared. There we go. Times then the integral over the solid angle of then the modulus of the Ylms squared. Now, since this is equal to 1, that means this term here has to be equal to 1, and this term here has to be equal to 1. So it has to be true then is, again, these two things have to be normalized separately. So I have to have the integral of dr r squared, normalization of r. But since this is also equal to u over r, so this is also equal to the integral of dr, simply modulus squared of u, must be equal to 1. And simultaneously, I have to have the integral of d omega, the modulus of the Ylms squared, equal to 1. So Again, the nice thing about the normalization condition here is that, again, since this thing has to be equal to 1, but again, since this is a radial piece which is separated from the angular piece, this thing can split up into 2 different integrals. So each one of these integrals then have to be normalized basically independently from each other. So for here, I can either look at the r or the u. It's actually a little bit easier if we look at u. And then here, this has to do with the Ylms, where again, inside of this integral here, this is then the probability. There we go. Finding the particle, or in this case, the 2-body, within d omega at angles theta and phi. So good. So that's one really nice thing about this. So again, our normalization condition just says that we can normalize each one of these pieces independently, since each one is simply equal to 1. So good. So last thing is the derivation of the Ylms. I'm not going to bother going through that because we actually already saw that in math methods. So I'm going to skip all that and basically just talk about some properties. So let's talk about some properties of the Ylms. If you want to go through and remember, again, all of that's going to be in the book. So I'll let you go ahead and go through that. But otherwise, we actually already did that in math methods, so I'm not going to bother. So first things first is whenever we have a negative m, so YL of negative m of theta phi is actually related to the Ylms by the complex conjugate of it. So this is equal to negative 1m times YLm star theta phi. Which basically means that if I reverse solve this, that means that the complex conjugate of the Ylms is actually equal to then negative 1 to the nth power of then YL negative m. So that's that guy. And then the last property that's going to be useful to us is if we integrate over the solid angle of then YLm theta phi times then YL prime m prime star theta phi, then this is actually equal to the Kronecker delta function between L and L prime and the Kronecker delta function between m and m prime. So basically it just means that if I integrate over the solid angle, this thing is only non-zero when L and m are both the same. Otherwise, this thing is equal to 0. And the reason for that, as we talked about in math methods, is that these guys can form a complete orthonormal basis. So again, these guys are the basis functions of the 2-sphere, which forms a complete set of orthonormal basis functions. So basically when you're doing problems involving things like this, what you want to do is, so if I gave you some random type basis, what you basically want to do is, or wave function, you want to turn that wave function basically into the Ylms, and then use this property of the Ylms to then basically get rid of a whole bunch of terms. So basically this property is actually a very useful property, and the fact that these guys are orthonormal to each other, and the only ones that survive are the ones which are in the same direction. So good. So that's the end of this chapter. Life is great. So basically next time, on Thursday, we'll do one small little part of the next chapter, which basically has to do with finally saying that we have the hydrogen atom. So here, basically all we're going to do is we go back to our problem, we're basically just going to set this guy equal to the Coulombic potential. Now, a lot of this chapter, actually, the quantization of it, of the hydrogen atom, we actually already did in math methods. So we get to skip a lot of that. So we can just talk about the radial function and do all that kind of good stuff using those results. Okay, so we don't have to actually necessarily go through and do all that. Show the surprising thing that the quantization comes from the fact that you have to do a, as we did in math methods. So basically what happens is you can't sum over all possible values, because in that case, your wave function can't be normalizable. So basically you have to terminate your sum. You have to truncate it at a particular point, which then depends on the n and the L values. So it's kind of remind you what we talked about in math methods. But that's kind of the, basically, that's where the quantization comes from, is that we can't sum over all infinite possible states. We have to truncate it at some particular point when the numerator goes to 0, and that gives us the Guerre type polynomial instead of an infinite sum. So that's where the quantization comes from. But again, you already saw that in math methods. It'll be in the book if you want to remind yourself. But yeah, so that's what we'll talk about next time. So the hydrogen atom. So how are we doing?
I'm still here.
There you go. You're always so full of optimism there.
Yeah.
Clayton, how are you doing?
I'm just very tired.
You were very what?
Tired.
Oh, nice. Well, all the videos that we have had, so I probably should have told you guys this before, but all the times we've met on Zoom, I've actually recorded all those videos and I put them up onto YouTube.
Okay.
So anytime you want to go back and watch any of those, so basically just go to YouTube and then search my name, and then you can find the videos on there. So if you want to rewatch what we actually did here, I'll probably post that within the next day or so. So you can go back and rewatch, yeah, in case you missed something. So maybe it'll make more sense the second time. All right, so any questions at this stage? You guys doing okay?
I do have a, I was going to ask you about the project with the laser, if you've got a minute for that.
Okay, we'll get there in a second. So any quantum questions?
That I don't think I have.
No. Okay, good. So as far as quantum is concerned, then we'll end the class here, and then I'll see you guys on Thursday, and then I'll talk to you about the laser. Okay. So we'll see you later, Clayton.
All right. See ya.
See ya.